microevolution. We just have literally a few slides left. We talked about I think last time we left off talking about this fish, right? We talked about how natural selection, so we kind of know how natural selection works. We know that it weeds out alleles that are bad, and it tries to promote alleles that are what? That are good. So if you think to your example of a cheetah, any allele or any genetic mutation that gives you increased speed would be an advantage. And natural selection would probably favor that. But remember here, the thing about what it favors is not so clear. Because what is being favored depends on what? What was that? What is being favored depends on the number of individuals. So if you have a lot of individuals that are right-jawed, who has the advantage? Why? Because if there's more right-jawed individuals, then your prey is going to be constantly being attacked on the left side, making the right side vulnerable, giving the advantage to the left-jawed version. Right? So what happens then is, we talked about the left-jawed version will increase in frequency, but then the advantage shifts. Then the left-jawed version has a disadvantage as they become more popular. So that's where we left off. So there's a gene that determines the slant of the mouth, and the two alleles are either going to be right or left. Okay? I'm not really sure about the inheritance pattern, if it's dominant or recessive, but what this is saying is that there's a lot of right-jawed versions. The left-jawed version has the advantage. So here, natural selection is a little bit funny because we really don't know which allele is better unless you know which one there is more of. Okay? Now, I want to talk about sickle cell for a second, because remember in the example of the Hardy Weinberg that we just did a little while ago, it talked about in some populations of the world, the allele frequency is 15%. So, in other populations, it's really, really low, closer to 0. Why is it high in some and low in others? Here is a map. Okay? This is a map of the sickle cell allele. So you can see that it's pretty high in certain areas. In other areas, we don't see any red. It's very, very low. It's white. So the allele frequency is very close to 0. Now, we also look at where we find malaria. Now, do you know what malaria is? Yeah. It's a disease caused by a parasite. Okay? Parasite gets into your blood, attacks your red blood cells. It's transmitted by a mosquito. Okay? Now, you'll notice, especially, there's a very strong correlation in Africa. You'll notice where there is high incidence of malaria, there is generally high incidence of the sickle cell allele. Now, the question is why? I've taught you that sickle cell is good or bad. Very good. You guys are getting smart. Normally, we think that, given the choice, I would not want to have sickle cell. You never want to have sickle cell disease. But what would happen if you had one copy of the allele? Do you have the disease? No. Okay. So here, let me paint this little picture for you, okay? If you have one copy of the disease, you are normal. If you live in an area of where there's malaria, you actually have an advantage. Because, here's the thing. The parasite, for some reason, it's not really clear why, but for some reason, the parasite does not do well in individuals that are heterozygous for sickle cell. If you're normal, That's great. That's beautiful. You have beautiful red blood cells. But the problem is if you get malaria, you might be in big trouble. If you have sickle cell disease, that ain't good because you can't carry the oxygen properly. Your blood doesn't move properly. That ain't good. If you're in the middle, if you're heterozygous though, and you're living in an area where there's a lot of malaria, you actually have an advantage over either genotype because you're healthy enough and you're also resistant to malaria. We call that the heterozygote advantage. Okay? If having two different copies of an allele gives you an advantage and natural selection favors it, we call it the heterozygote advantage. Now, cystic fibrosis may be another example. What happens in cystic fibrosis? Can we talk about that? What happens in your lungs? Why? Because your cells retain too much what? Right, very good. They retain a lot of salt and they retain a lot of water. They pull the water out of the mucus and the mucus becomes very thick. So, in other words, a person with cystic fibrosis retains more water than someone who doesn't have it. That's a problem for the mucus. Well, what would happen if you had one copy? Are you normal? Okay, so very well, probably what happens is you retain slightly more water than another person that doesn't have the other copy that's homozygous normal, but you're still fine. You're still normal enough, right? But what would happen if you're living in an area where there's diarrhea? Imagine you're living in an area where the water is infected with a parasite that causes diarrhea. Diarrhea is symptoms of many diseases. What's the problem with diarrhea? What do you lose? Too much water. So, if you're heterozygous for cystic fibrosis, you have one copy of the allele, you're normal, and you retain more water, do you have an advantage in that environment? The answer is yes. What's the problem with iron overload? Well, we take it for granted that you can go to the store and buy whatever you want nowadays. You got to think back, our ancestors, you know, there may have been times where food may have been very scarce. So maybe they weren't getting enough iron in their diet. If you're heterozygous for iron overload, that means that you absorb more iron than a normal person. If you absorb too much iron, that ain't good. You can get really sick. If you don't have enough iron, that ain't good either. You can't make enough hemoglobin. But if you're heterozygous and you're not getting enough iron in your diet, then you could absorb more iron than someone who isn't heterozygous. Again, you have an advantage, okay? So if the heterozygote has an advantage, that's called a heterozygote advantage. Yeah, Claudia. How do I gotta press pause? All right. So, I think I'm almost done. Almost. Hold on. I just got two little mini stories as we go through this unit, which I know for some of you is very painful. One, you're probably getting really smart and you're starting to realize when I ask you questions, you kind of know like the answer. Now you know. Now you know if I ask you a question, you're gonna be like, it depends, right? So if I say to you, is it better to be a poisonous plant or a non-poisonous plant? What would you tell me? And that's often the case because in evolution, there are always trade-offs. I shouldn't say always, but often there are trade-offs. So here's a graph. This is a plant that can make poison, okay? The red are poison-producing, cyanide-producing plants. The white are non-poison plants. You'll notice there's a lot of red here, and as we go this way, less red, more white. It turns out you can make cyanide, you freeze more, you're more likely to freeze than a plant I don't know why. Than a plant who doesn't make cyanide. So what's the trade-off here? Right. If you're living in a colder area, it's better not to make cyanide. So what I'm telling the message here is, what may be good in one environment may not be so good in another environment. So that ends up with the last story, which is my favorite. How many of you know about this bird? What happened to this bird? Why? Why did it go extinct? Sabrina? Aha. So what? Now I want to ask, what is this? It's a bird. How do you know it's a bird? It has wings. It has feathers. Is a defining characteristic of a bird flight? No, not all birds fly. Do you think this bird flew though at one point in its evolutionary history? It had to because it has wings, right? So we know that birds, even flightless birds, must have evolved from birds that could fly. It's another example of a reversal. Birds evolved flight, and then some of them reversed that and became flightless. It's like whales, right? What happened to this bird is it found its way on an island that had no predators. Now, I'm going to ask you a question. What's the advantage of flight? You can escape things, right? Well, what if there's no predators? Imagine there's no predators on this island. You have these beautiful large wings, and I don't. Here's the thing. When you have beautiful large wings, you need big muscles to power them. That takes a lot of energy to feed those muscles. So you may have these big, powerful wings that have no advantage. Guess what evolution favors in that case? Any mutation that reduces the size of the wings, because that means you don't need to spend as much energy in building these massive wings. You could spend more energy in making babies. At the moment, so at a particular moment in time, for the dodo bird, it was an advantage to actually evolve in the direction of being flightless. But that's when the island had no what? Predators. Then at some point, Portuguese sailors arrived with all of their animals, and they called the bird the dodo bird because it acted very stupid. It would literally go up to these sailors because it didn't know any better. The problem wasn't so much the sailors killing them. It was, if you're a flightless bird, where's your nest? On the ground. Now, your babies are vulnerable. What happened here was, in one environment, what may be good in one environment can be really, really bad if the environment changes. Think big dinosaurs. It's great to be big, but when that asteroid hit, plants started to die off, and you couldn't find enough food, being big ain't good. Okay? So next time we talk about big change. That is, hold on, the